So I'm going to continue with the example I left off with in the last video. I've got my calculator out so that we can do some calculations. I've extended the table out so that you can see, maybe I'll shift this a little, so you can see the formula as I fill it in and the final amount in the account for each number of compounds. I've started this already, but just to start filling things in. So here's the formula. The principal we said was going to be $5,000. That gets plugged in. The R is 2% interest. Remember, 2% is really 0.02 in decimal form. And then the N value, because this is annual compounding, the N value has to be 1, so that goes in both those positions. And then the T value is 3 years. Now, on our calculator, when we plug this in, start with the 5,000. Now the base here is all the stuff in parentheses. So we're going to put a parenthesis, a 1 plus 0.02. Now generally you would want to divide by 1 here. So I'm going to go ahead and do that, even though you don't have to. For this one, I'm just going to type it in so you can see what it looks like on the calculator. Then you're going to raise to a power, and I'm going to make that power 1 times 3 again, just so you can see what's going on. Now, my calculator uses a superscript notation for the exponent, and I have to hit the right arrow to pop out of that exponent. Some of you don't have that, and it's just going to put a little caret, little arrow symbol there for the exponent. And if that's the case, then you may want to surround the 1 and the 3 with an extra set of parentheses, otherwise it won't put the 3 in the exponent. So you just want to be very careful there when you compute these things. If you did it correctly, you should get a final amount of $5,306.04. Almost didn't fit that on. Okay. So that means you would have earned $306.04 in that 3-year period under this compounding scenario. Now if I change that to semi-annually, that's an N value of 2, then on the calculator we switch this 1 and this 1 both to 2's. Now to do that, if you hit the second button and then the enter button, it will copy and paste the last calculation you made. And then you can go back, well, what am I doing? You can go back and change those 1's to 2's rather than trying to type the whole thing in. And I'm going to get a new value a little bigger, so let me I'll write in what it would be on the formula. 5,000, 1 plus 0.02 over 2 raised to the 2 times 3 power. And that turns out to be $5,307.60 right, if I round to the nearest penny. I can continue this on. We'll do this with quarterly. So again, I hit second enter, copies the previous calculation, and change the 2's to 4's. And I'm going to get 5,308.39 when I round it. Now I could go through and fill in the formula. I think you guys probably see the pattern now. You're just filling in the values, the P, R, N, and T. And so rather than write all that out, you'll see it develop on the calculator as we go. Alright, maybe I'll just do 1 or 2 more on the calculator. I've also pre-calculated these, so I'm just going to fill in the rest of the table in a moment. If I do this monthly and then weekly, I'll hit second, enter. Now just a little calculator practice. If I want to change this 4 to a 12, I need 2 digits instead of 1. So I'm going to hit the 1 for the 12. But if I hit a 2, I'm going to type over the top of the parenthesis, which I don't want to do. Instead, I want to insert a 2 in there, so I hit second. Maybe it'd be better if you could see this. I hit the second button and then the insert, or it's delete, but the second feature is insert. you put a 2 and it moves the parenthesis instead of typing over it. You can do the same for the 4 up on top there. Type a 1 and then insert a 2, and that will give you 12 times 3 up top. In the end, you'll get $5,308.92. Right, if we round that off. Okay, so anyway, you can kind of see how to continue calculating these. But what I want to do now is just kind of fill in with values I've already previously calculated, just so you can see how this plays out. And so that was the 12, right? Then the 52, that one, the weekly, that becomes $5,309.12. So it's going up a little bit more. And then you've got the daily value, which would be $5,309.17. The hourly value, which is $5,309.18. And when you round these off to the nearest penny, what you'll find is at this point they round to the same thing every time. Alright. Now the values are slightly different, but they're different farther out in the decimals. And so when you round to the nearest hundredths place, they round to the same thing. Okay. What's interesting is that at the beginning you have a very small jump in the end value, right, from 1 to 2 or 2 to 4, but it gives you a decently large jump in the output, right, about $1 jump or give or take. But as you get further up here, these increases get enormous, right? The difference from minutely to secondly is a matter of like 31 million, and yet it hardly changes the amount. In fact, it doesn't change it enough to change it at the hundredths place. It changes it out here at the, I don't know, 10,000ths place or something. It's way out there. Okay, so what we end up with is some sort of asymptotic behavior. What that means is that these numbers approach a certain value. And what's interesting is that using a little bit of calculus, which we won't get into the details of too much, you can actually determine what happens if you were to compound the money at every single moment, which you would consider basically an infinite number of times. Okay, and so if you continue this pattern on, we call it continuous compounding. And continuous compounding is essentially an n value that approaches infinity. It's not exactly infinity because you can't plug in infinity. That's why I'm drawing an arrow there, because we usually represent moving toward infinity with an arrow, not equaling infinity. And so there is a formula for this, continuous compounding, and it deals, you have to do a little bit of calculus to do that, but you're essentially finding the horizontal asymptote to this original function. And what you end up with is a new formula where a is equal to the principal times, now instead of this weird base, the new formula is going to have a base of e. You'll remember that exponential number we talked about on Wednesday of last week. That e value is our new base, and then instead of nt for the power, now n is not going to be used, we're actually going to have a power of rt. Okay. Again, I can't explain all the details of how that's derived because it does take some mathematics that we haven't seen yet, and we don't access in this course. Now, if I wanted to calculate this particular scenario for continuous compounding, I could do that simply by plugging in the 5,000 multiplied by e raised to the power of 0.02 times 3. Right? 0.02 is my rate, 3 is the years. And if I put that in the calculator, let's put that in up here, that's 5,000 times E. Now E, there's a button on your calculator right above, I gotta slide this up, right above the natural log here. If you hit second and then the ln, you get an E with a power. And in that power you want to put 0.02 times 3. And that should give us the maximum. This is kind of like the greatest possible outcome for, you see that, I pulled this away, I should have done that. It's the greatest possible outcome for compound interest. So it's still 5,309.18. Now, again, the decimal places to the right of the 8 are really the only thing that changes. You can see here, if we round it to the 8, they'll be the same. So the decimal places